Okay, hello everyone. It's a great pleasure to have Ethan Lake as our speaker today. Ethan is currently a postdoc at Berkeley. I think he is currently in Japan.
That's
Uh,
right.
So Ethan is a famous genius. When he was still an undergraduate student, he already carried out a lot of physics research in many fields, including not only condensed matter, but also like astrophysics. In particular, his research at that time in condensed matter was already very influential. In particular, his work on crystalline topological phases. And then when he moved to uh, PhD, he also studied many more other topics like marine materials, quantum criticality, and so on. I think now Ethan is very interested in quantum dynamics, quantum memory, and today this is the topic that he's telling us. Ethan, please go ahead.
Yeah, okay. Thanks, Leojun, for the kind of embarrassing introduction, but thank you. And yeah, I'm excited to tell you guys about stuff I've been thinking about recently. Actually, when I was thinking about what to talk about at this talk, I was kind of going back and forth between talking about quantum memories and classical memories. And at the end, I chose to talk about the classical memories. So we're going to be talking about um, classical error correction and non-equilibrium dynamics today. The talk is hopefully going to be at sort of a high enough level that it's followable by a diverse audience, but please, if anyone has questions, just interrupt me. I know it's a little bit awkward to do over Zoom, but hopefully it works out. Okay, so let's get started. What we're going to talk about today is kind of falls under the purview of what I'm calling many body memories. So we're going to be interested in physical systems that are capable of robustly protecting information against the effects of a noisy environment. So the inspiration for thinking about this question, well, it's kind of we're drawing inspiration from multiple different sources. One is, of course, quantum error correction. So this is how I got into the field of thinking about many body memories. It was from working on quantum error correction and being inspired by the advances in both the experimental and theoretical aspects of quantum error correction. Uh, Maybe a little bit less familiar to people in this talk are also some advances in machine learning and computer vision. These will show up later in the talk, but mostly these we're going to take inspiration from some techniques that have developed and been developed in these communities. Uh, and then on the physics side, perhaps the biggest inspiration for me recently has been learning about biological systems and the way in which information is processed in the natural world. So the natural world is full of many fascinating examples of biological systems that have learned to process and store information in robust ways. And I think we can, as physicists, get a lot of inspiration from turning to that area. Um, so what are we actually going to do? Well, we're going to be focusing on the physics of classical many-body memories in this talk. Okay, so we're not going to be doing any quantum mechanics in the whole talk. I think we're still. I'm doing this because, as you'll see, I think just the physics of classical memories is very far from being understood and extremely rich. Um, and since we're going to be thinking about the physics of many body memories, we're not going to be just thinking about any random error correcting code. We're going to be thinking about dynamics, which is, of course, spatially local, hopefully in a small number of dimensions. We're going to be thinking about dynamics, which doesn't require any fine tuning to operate. And of course, we'll also be trying to look at dynamics, which is interesting from a physics or a statistical physics point of view. Okay, so that's what to expect. Um, the general setting in which we're going to be thinking about these questions is that of cellular automata. So I'm just going to briefly review what this is. So a cellular automaton is essentially a spin model defined on a lattice. It's usually defined in discrete time. And how it works is that at each time step, each spin updates according to some in general, probabilistic rule that's determined by the states of its neighboring spins. Okay, so spins on a lattice, they look toward their neighbors and they update in some according to some function of their neighbors. So people who have played around with cellular automata will recognize some of these examples. Rule 90 is a famous one-dimensional cellular automata shown on the left, introduced by Wolfram. There's the game of life, which has kind of made its way into the popular imagination. And for my purposes, the good old 2D Ising model is also a cellular automaton. Cool. And in particular, we're going to study the following type of dynamics. So recall what we're interested in today is noise robustness of local dynamics. And so we're going to consider cellular automata in the presence of a bit of noise. For us, the noise is going to be characterized by two parameters. So the first parameter, P, is the strength of the noise. And the second parameter, eta, is the bias of the noise. How this works is that at each time step, a given spin will either become what it's supposed to become under the cellular automaton update rule with probability 1 minus P, or with this probability indicated on the screen, it will become plus minus 1. Okay, so here's what's happening is that when the bias is plus 1, the noise just likes to turn all of the spins into plus 1. When the bias is 0, the noise just randomizes the spin. And when the bias is negative 1, the noise likes to turn all the spins into minus 1. Okay, so this is the kind of model of dynamics we'll be thinking about. And what we want to do is we want to find cellular automaton that maintain memory, so they robustly store information in an open subset of the P eta plane. Okay, what this means is that we want to find dynamics which can robustly store information without any fine tuning. Okay, so this is the goal. Yeah.
Is this model already kind of containing some fine tuning?
It doesn't contain any fine tuning in the sense that all of the transitions from one state to another are allowed and have non-zero probability. So you can get from something that would involve fine tuning is to say like the dynamics has to respect some particular symmetry, or the dynamics can only flip your spin to this value if the other spins in its neighborhood satisfy some condition, right?
But this is a particular type of noise.
Yeah, this is a particular type of noise. This is done for some. Okay, so in the talk, you can think of this particular type of noise. If you're not happy with this particular very simple IID noise model, the results will hold for any noise model which is called a p-bounded noise model, meaning that it's some kind of technical definition, but any dynamics which is obtained by, say, coupling a system weakly to an environment, no matter what the nature of that environment is or the nature of the system environment coupling, will fall within the framework of the results we're going to consider.
I see. This part is understood.
This part is understood, but it's not going to be discussed explicitly in the talk.
Thanks.
So the talk is just going to be IID noise of a particular bias. And if you'd like to learn how to go beyond that assumption, I can tell you in detail later.
Thanks.
Yeah, no problem. So the literature in the field of cellular automaton is full of cellular automaton which do really amazing things. In fact, as Liujin said, I'm currently in Japan. I'm here for a conference on artificial life and AI and stuff. And this conference has just been full of people coming up with cellular automaton which do the things like the craziest things you could possibly imagine. But unfortunately, essentially every cellular automaton in the literature is fine-tuned. Okay, in the sense that if you add just a little bit of noise, it breaks, or if you add a little bit of bias to the noise, it breaks. Okay, so let's go through some examples. So the example relevant for us as physicists is, say, the Ising model in greater than one dimension, right? Here, the x-axis is P, which the noise strength, which you can kind of think of as being temperature, and the vertical axis is the noise bias, which you can think of as being an external magnetic field, right? And we're familiar with the fact that the Ising model maintains an ordered phase only when the external magnetic field, i.e., the noise bias, is zero, right? So in the Ising model, you can store one bit of information for a long time, provided that the bias of the noise is precisely zero. But as soon as you break the symmetry, the ability to robustly store information goes away. Okay, so the Ising model requires fine tuning. Another fun example is the game of life. Okay, so here I'm just showing an animation of the game of life. People may be familiar with this particular structure. What's going on here is I've chose a particular initial condition that produces this marching army of gliders that go and move across the screen, right? And one can imagine taking these things and combining them in different ways to produce all sorts of crazy emergent phenomena, right? So, for example, you can use these kinds of devices to build a Turing machine, right? So there's a lot of amazing structure in the game of life, but it's very fine-tuned. So in the next slide, I'm going to show you what happens when we start from the same initial condition, but we add noise of strength 10 to the minus 5. Okay, so there's a 10 to the minus 5 chance that each bit flips at any given time step. Okay, so hopefully you can see that everything has been destroyed. Our ability to produce this stream of these gliders has been completely killed, even though we're at an extremely weak noise strength, right? Here we even see a little glider that's coming back in the opposite direction. Okay. So there's no noise robustness here, even though the phenomena is very interesting. Another way that the game of life is not robust is that requires that the updates made to the system be completely synchronized across all space-time locations. Okay, so what's happening here is that at every time step of the animation, every single cell is updating at precisely the exact same time. Especially from a statistical physics point of view, this is not realistic, right? If I have 10 to the 23 particles in a box and they're all getting updated according to some statistical process, there's no way that they're all going to be, updating at exactly the same time in lockstep. So when we make the updates asynchronous, we also see that everything is destroyed. Okay, so this is kind of interesting what's happening, but we can definitely not use the game of life to store or process information when the updates are made asynchronous. And these phenomena are generic in most of the cellular automata constructed in the literature. Okay, so it turns out that coming up with a local and asynchronous robust memory is actually very hard. The reason is that in order to preserve information, we need to perform error correction in a distributed collective way. Okay, so the error correction process needs to self-organize from a collection of components which are too small to individually understand what process is being undertaken, right? And in fact, before this work, there were only 2 examples of noise robust cellular automata known in the literature. So since there are only 2, I'm just going to briefly discuss what they are. The first one is called Tomb's rule, which has been around since 1969. And it's an extremely simple cellular automata defined in the following way. So at each time step, a spin at site I gets sent to the majority vote of itself, its eastern neighbor, and its northern neighbor. Okay, this being defined in 2 dimensions. Tomb was able to give a pretty complicated, honestly, proof that this rule defines a robust memory, provided that the updates were synchronous. And he was able to show that as long as the noise strength is sufficiently small, this rule is able to stabilize 1 bit of information for a thermodynamically long time. Okay, that's one example. The other known example so far was a automaton constructed by the mathematician Peter Gatch, whose construction first appeared in 1989, but which has been continued to be updated until until the present. And Gatch gave an extremely complicated construction that was claimed to produce a robust memory in one dimension. Okay. This is interesting, if a bit provocative, because we know that in equilibrium, maintaining information in one dimension is impossible, right? There are no equilibrium phase transitions in one dimension with local interactions. Unfortunately, Gatch's automaton is so complicated that even checking it numerically has proven to be impossible. So, for example, if you flip to page 189 of his paper, you'll find algorithm 19.7, which is one of about 100 algorithms defining his automata, and it's a mess, right? You have things are being legalized, there are germs which are being doomed and everything, and it's impossible to understand. When you read his paper, you feel like you're reading the description of the full description of the working of a cell written by a computer scientist. Okay, it's unfortunately completely intractable. Okay, so that's it. So we just have those two examples, and this means that there's really been no progress on understanding the physics of noise robust phases of matter in 50 years, right? So Toombs' rule is the only example that we understand, and that was introduced back in 1969. So the kind of questions that I was asking myself going into doing this work was, okay, well, why is this, right? So can we, for example, understand the universal underlying mechanisms that enable us to perform error correction in local systems? And if so, maybe we can construct new examples and perhaps even learn new things about non-equilibrium dynamics. Okay, so that's what we're going to do in this talk. The talk is going to be split into two parts. I may only get to talk about the first part depending on time. So we'll start with that. The first part is going to be on a work that was posted recently with Soohan Roh, who's a soft matter faculty at Harvard. Here's a brief summary. I'm just going to jump right into it. Okay. So in what follows, we're going to consider mostly two-dimensional memories, and we're only going to consider memories which protect one logical bit of information. And in addition, the logical information is going to be extremely simple. So the information is going to be encoded in two states, either the all spins up state or the all spins down state. Okay, so just the logical states of the two-dimensional repetition code. Let me now kind of try to illustrate why engineering a robust memory is difficult. Okay, so to do that, consider the following situation where we have a logical state, mostly white spins, and we insert a large error, okay, by flipping all of the spins within a particular bubble to be the opposite sign. Okay, if we're going to have a robust memory, this error needs to be identified and corrected. Okay, the problem arises when this error gets very large. So imagine the limit where this droplet of errors is thermodynamically large. Okay, now zoom in to the boundary of this error. Since this error is very large, when you look at it at the boundary, it kind of just looks like a straight, flat domain wall interface, right? And now we run into the following problem, right? The dynamics, since it is local, cannot actually figure out which side of this domain wall is the inside and which is the outside, right? In order to be able to get rid of this error, we need to know that, oh, the black spins here are the error and the white spins are the logical state. But if we just look locally, we have no way of distinguishing the two, right? Now, this becomes a problem when we add biased noise, which favors the spins in the error, right? So if I add a little bit of biased noise that favors the spins to be black, then this error is just going to ballistically expand because of that, right? And in particular, we're not going to have enough time to wait around and figure out which side of the domain wall is the inside and which is the outside. Okay, so this is the reason why, for example, the 2D Ising model is not robust when we add a little bit of a bias that favors one particular sign of the magnetization. Okay, I hope that.
I have a quick question. So can
Yes.
I tell whether it's inside or outside by its concave or convex? Like we can define some local rule and try to make
Right.
everything become more concave, for example.
Right. That's exactly what the Ising model does, right? The Ising model says that having a domain wall is energetically bad. And so if you see a domain wall that's curved, you want to eliminate it by making it smaller. And you use the curvature of the domain wall to do that. The problem is that when you have very large errors, their curvature is zero. Their curvature is very small, right? Curvature is like the inverse size of the error. And you can argue that the typical size of the largest minority domain in your system that will be created by the noise is like the logarithm of the system size. So in particular, in the thermodynamic limit, you'll have to correct errors which are thermodynamically large, okay, whose size diverges in the thermodynamic limit. Uh, Given that, relying on the curvature of the domain seems is basically a no-go. Right?
I see. Thank
Uh,
you.
yeah, so we have to come up with a slightly different way of doing it. I'll show you how to do that just in just a moment. Okay, cool. So how then is error correction possible, right, with regards to this question? Well, here's one answer. We're actually not going to try to figure out which side of the domain is the inside and which is the outside. All we're going to do is we're going to squeeze the domain in the following way. Okay, so we're going to consider rules. We're going to consider dynamics that works like this: the plus spins infect their neighbors in the vertical directions, and the minus spins infect their neighbors in the horizontal directions. Okay, so this is not really based on domain walls anymore. We're just thinking about the plus spins trying to turn other spins to be plus in the vertical directions, and likewise for the minus spins. Okay, so let's think about what happens under this dynamics, right? Now, in the situation where on the screen where I have a minority minus domain, well, the plus spins are trying to expand from the vertical directions, and so the minus minority domain is going to get shrunk from the vertical directions. Of course, the minus spins also expand horizontally, so this minority domain is going to get bigger along the horizontal direction. But the fact that it's always getting smaller along the vertical direction means that it will eventually be eliminated. Okay, so it kind of gets pancaked like this. Right? Notice we're not trying to figure out which side of the domain wall is inside and which one is outside. We're just committing to moving the domain walls ballistically in this particular fashion. Okay, so the similar thing is true for the other type of domain wall, right? The other type of minority domain, excuse me. It's squeezed in this particular direction. So it becomes progressively skinnier and skinnier until it's eliminated. Okay, so I'm going to show you some movies of how this works in just a second. But in order to make this a little bit more precise, let me just formalize this a little bit. Okay, so the concrete update rules that we'll be thinking about are as follows. We're going to consider update rules where the central spin in a 3x3 grid does the following. With 50% probability, it becomes -1 if either of these minus squares are -1. And with the other 50% probability, it becomes +1 if either of the vertical neighbors are +1. Okay, so I hope that that definition makes sense, right? So these are the concrete rules that we'll be looking at. Notice that this dynamics has a symmetry under a combination of a spin flip and a rotation, right? So the spin flip is exchanging the plus and minus, and the rotation by pi/2 exchanges the vertical with the horizontal orientation. Okay, so this sort of intertwined spatial and internal symmetry is the only symmetry of this dynamics. Okay, so that's the rule. So let's look to see what it does. First, I'm going to show you what happens when the updates are made in a synchronous way. So, like I said, from a stat mech point of view, this is not realistic. Maybe from like a quantum circuits point of view, it's realistic, but for stat mech, not really. So we're just going to look at what happens. Okay, what happens is precisely what we said would happen. It gets squeezed in as follows. Okay, now we go to asynchronous dynamics. Here I'm just going to be randomly choosing sites at which this rule is to be applied. And you can see that the error correction is still happening. The squeezing of the domain is still being accomplished. It's not as fast because it's a little bit rough around the edges because of asynchronicity, but nevertheless, the dynamics is still managing to autonomously correct this error. Okay,
Question?
now, yes.
In the second case, is there some interesting pattern along the boundaries of the black region?
Yeah, actually, I haven't characterized the roughness of that boundary yet. I think from a StatMech point of view, that's a very natural thing to do, and it hasn't been done yet. I'll show you some kind of like an action for the magnetization from which that could perhaps be studied, but I haven't looked into it yet. That question is even more striking in a few other kinds of examples that I'll define on the next slide.
And also, can I view this process as some kind of reaction diffusion dynamics?
Yeah. Well,
Uh,
I'll show you well, there's only kind of one field in which the you the dynamics is described by sort of a partial differential equation in one single variable rather than having multiple different types of reactants interacting with each other. But I'll write down that equation on a future slide.
Thanks.
Yeah. Yeah, thank you. So in this slide, I'm just going to define a couple different families of error correcting dynamics, which as we'll see, have kind of a bit of different physics. So the dynamic we just described is on the left. I'm going to call it the R rule. R is for rotation. And then we can also define a couple of other rules by combining the spin flip with different symmetries of the lattice. Okay, so this F rule here, F is for flip, combines a spin flip with a reflection through this diagonal direction. The M rule combines a spin flip through a reflection about the horizontal plane, and this T rule just has a symmetry under a spin flip without any spatial intertwinement, without any spatial symmetry entry. Okay, so maybe the exact precise definition is not too important, but the thing to remember is that we have different types of symmetries that are being used in the dynamics. Okay, so let's look at some movies to see how they work. So first, with this F rule, we have a reflection about about a diagonal direction combined with a spin flip. Under synchronous dynamics, you can see that this minority domain is getting corrected in kind of a strange way. It's being squeezed, but it's also kind of getting sheared at the same time. Under asynchronous dynamics, this is what happens. So here, I think the Liu Jun's comment about the interface, how the roughness of the domain wall and understanding that physics is quite interesting. You can see that the domain wall on the top is quite rough indeed. The one on the bottom is more smooth, and yeah, understanding the precise physics at work here is something I think would be fun to work out. Okay, now the M automaton. So here again we have a reflection combined with a spin flip. This is synchronous. Again, there's some kind of squeezing, shearing thing that's being accomplished here, and asynchronous. I quite like this one. You can see that the bottom of the domain is sort of turning into this bonfire-like structure while the top of the domain remains quite sharply defined. And despite the sort of chaos that's going on here, the error is eventually corrected. Okay, finally we have this T automaton. So here under synchronous updates, this is what happens. For those of you familiar with Toom's rule, you'll recognize that this dynamics is qualitatively slightly similar to Toom's rule. Errors are being corrected, but okay. Now let's go to asynchronous dynamics. I'm not going to add any noise. I'm just going to run the error correcting dynamics asynchronously. Okay, so you can see that the entire system self-destructs. So when this automaton is made asynchronous, it completely loses its ability to correct errors. And even in the absence of noise, it immediately produces a featureless disordered state. Okay, so the role of synchronicity is indeed quite powerful in certain circumstances. Okay. Now, okay, what can we, the videos are nice, but what can we say about these memories? Well, we can first prove the following theorem. We show that all of these squeezing codes, all of these different memories that I just defined, are robust memories, provided that they are updated synchronously. So what this means is that there's always a order one value of the noise strength, where if you're below that value of the noise strength, you can remember information for a thermodynamically long time. Okay, and this doesn't require any fine-tuning of the noise distribution. This theorem is valid for this kind of very general type of noise models that I was talking about in response to Liu Jun's earlier question. Okay. I don't think I want to spend a lot of time on the proof, although I'm happy to take questions about it if people are interested. It relies on some old results by Tomb, and it's technically not super sophisticated, but maybe a little bit tedious. So I'm gonna skip the discussion.
Hey, Ethan, I have another question. So,
Yeah.
given your simulation, how do you determine what is the error and what is the information? Does it based on the total area, or does it based on the topology? For example, you consider some simply connected error. If I try to change the shape, like is a loop-like or other shape, does it got corrected or not?
So you want to know, like, if I started from a configuration like this where I had a loop of flip spins going across the system, what would happen?
Right. Yes. Yes.
Yeah, that's the principal failure mode of these memories. So uh, unfortunately I don't have the animation for you, although I can show you later when I'll have an interactive demo later that we can look at this question in. But a logical error is produced by a homologically non-trivial strip of minority spins forming across the system. These I'm not aware of any cellular automaton which is able to correct homologically non-trivial errors. This turns out
So
to
here
imply
you assume the torus, right? Is the torus structure important?
it's not important for determining the lifetime of the memory, no. But yeah, your comment about basically when you have a string of errors which contiguously spans from one boundary to another boundary, that has the possibility of producing a logical error. Anything less than that won't produce a logical error.
I see.
And that fact actually means that that kind of shows that the memory lifetime in these systems is like an exponential in L, where L is the linear system size. It's not e to the L squared, which is like the distance of the repetition code, right? So we're not correcting errors up to the code distance. We're correcting errors up to the square root of the code distance. But that's the best that we can do in terms of constructions that I'm familiar with.
Oh, thank you.
Yeah, no problem. Cool. So this theorem is for synchronous updates, right? Proving things asynchronously is a little bit difficult, particularly in light of this example where we saw that asynchronicity completely destroyed everything. Okay. So for asynchronous updates, the easiest thing to do is just to check numerically. So we're going to go back to the first squeezing code that we introduced. Now we're going to consider asynchronous updates, and we're going to add a little bit of noise. So here the noise is going to be at a strength of 1.5%. Okay, so you can see that, well, the error is still being corrected. The correction process is slowed down by the existence of the noise, but it's still getting there. So except for this one that just completely killed itself in the presence of asynchronicity, all of the squeezing codes that I introduced turned out to have a threshold at a finite value of the noise strength, meaning they are all many body memories at a sufficiently weak value of the noise. Okay, so there are numeric, so one can run numerics computing the logical failure rate and do a scaling collapse on them in a standard way and identify the presence of a phase transition. The phase diagram that one obtains from this process looks like this. So here I'm plotting the phase diagram as a function of the noise strength on the horizontal axis and the noise bias on the vertical axis. This blue region here is a memory, and the white region is just a trivial disordered phase. Okay? So as long as the noise strength is smaller than some particular constant, we have a memory. Okay, so we have some new memories. Why are they interesting? There are a few reasons. One reason is can be found by studying their coarsening dynamics. Okay, what we do here is we consider a quench from a random infinite temperature, if you like, initial state, and see how the dynamics coarsens to a logical state. Okay. Well, an immediate first result is that the coarsening is ballistic because the errors in the system are being corrected ballistically. Kind of to figure out other things that happen, we just have to, again, watch movies. So here we're going to look at the first squeezing code, this R model. I'm going to start from this random initial state, and I'm going to quench. The quench dynamics is described by this differential equation that I've written on the bottom. Okay, the dot dot dots are terms that would exist in an equilibrium, like Ising model type situation. Okay, so this is what happens. We can see that eventually we reach a logical state, and the coarsening actually happens rather quickly. So if people are familiar with this problem in the Ising model, or indeed in Tomb's rule, you'll know that there's actually a large probability of reaching a state which is not a logical state, which has a strip of magnetization. And you'll also know that it will take like a time of L squared in order to get to that state. And let's look at the other ones. So here, this one has a symmetry of a spin flip combined with a reflection. And you see what happens is that we have quenched into a state that exhibits flocking, essentially. So that minority band of the black spins that formed at the end of the animation is just sort of ballistically flocking across the system. So people who have studied active matter before will find many parallels of this phenomenon with the phenomena observed in, for example, the Toner 2 model or the active Ising model. Okay, likewise for this guy, M. What's happening here is, again, the formation of essentially a flock. Okay, so the way these coarsen is they don't always reach a logical state. Rather, they reach this kind of flock that moves around the system. If you're wondering whether or not the flocks can be used to encode information, the answer is yes. But I won't talk about that. Okay. Another interesting thing about these models is that they exhibit a phenomenon that I'm calling fluctuation stabilized order. Okay, so what is this? Well, in order to understand these phase diagrams, theoretically, when we do asynchronous updates, the first thing that any condensed matter physicist would do is to do mean field theory. Okay. So how that works is you write down a master equation for the dynamics of the spins. Okay, this can be done exactly. You then assume that correlation functions between the spins factorize in this way. So you assume that the expectation value of the product of spins on different sites is the product of the expectation values. And when you make this assumption, you produce some dynamical mean field equation that you can then analyze to obtain a phase diagram. Okay, what are the expectations from doing this? Well, this analysis is expected to be exact as the number of spatial dimensions goes to infinity, because fluctuations are weaker in higher dimensions. And it's expected to overestimate the stability of the ordered phase, right? This analysis drops fluctuations, and dropping fluctuations should enhance order. Okay, so what happens? Well, when you do this calculation for these dynamics, you find that their evolution is actually just described by this following equation. The magnetization simply relaxes exponentially quickly to the value set by the bias of the noise. There. So what this means is that all the error correction process in the dynamics is completely gone from mean field theory. Okay. In particular, it predicts that we have no ordering in mean field theory. So it predicts that ordering should get weaker in higher dimensions because mean field is exact in higher dimensions. And in fact, this is true. So you can do an extension of mean field called this cluster variational method to show that for the R squeezing code, the critical strength at which you get a memory, the critical noise strength, goes as 1 over d squared in d dimensions. While for the other ones, the F and the M, in fact, the critical noise strength is actually 0 in every dimension other than 2. Okay. So you have ordered phases that exist only in 2 dimensions, but then when you go to higher dimensions, they're destroyed because of the lack of fluctuations. Okay. So this is kind of a bizarre scenario where fluctuations stabilize order that I don't think has shown up in condensed matter physics before. So I think it'll be interesting to understand at a bit more of an intuitive level why this is happening. The other interesting thing is comes from looking at the phase transitions that arise in these models. So again, we have this kind of a phase diagram, and what I'm going to talk about in this talk is just the phase diagram the phase transition that occurs at the pink star. Okay, so the transition that occurs at 0 bias as the noise strength is tuned. Okay. Now along this line, one has a Z2 symmetry, which is the spin flip combined with some spatial symmetry. And you have one order parameter that is going critical at the transition, just the magnetization, right? So we can ask, what universality class is this phase transition in? Right. Now, when one does RG calculations, so one can do RG calculations in an out of equilibrium setting using some techniques that I'm not going to get into. You'll get the expectation that you should actually flow to the same fixed point as the 2D Ising model. Okay, this is known as model A dynamics for people who know about non-equilibrium phenomena. So, in particular, the breaking of detailed balance, the fact that we're out of equilibrium, is predicted to just be actually irrelevant at this critical point, and we'll just flow to an effectively equilibrium description. Now, this is actually what happens for Tomb's rule. So the other known example of a robust memory, even though Tomb's rule is very out of equilibrium, right at this critical point, it has the exact same correlations as that of the equilibrium 2D Ising model. Okay, and people have looked at this question, since the 90s and tried to find counterexamples, and it seems that we always get an equilibrium description. Okay, so what do we get in these models? Well, we just do the numerics and see what happens. Okay, so for the static correlation functions, just the spatial correlation functions, we find exponents which are close to, but maybe not exactly equal to those of the Ising model. Okay, so the plots on the screen are not important. It's just to show that the work was done, right? Close to, but not exactly equal. The story is very different when we look at dynamics. Okay, so here what is being plotted is the magnetization following a quench from the ordered state to the critical point. So we start with, say, all spins up, and then we turn on noise, which is exactly equal to the critical noise strength, and we see how the magnetization relaxes. Okay, so the magnetization in this setting is known to decay as a power of time, some scale invariant way, with the exponent of the power also being universal and determined by the exponents of model A dynamics. So what's shown in this plot is this for a few different examples. So the Ising model, the 2D Ising model, and Tomb's rule are shown as the gray and light green lines here. They have a dynamical exponent of slightly more than 2. And then the other squeezing codes that we studied in this work are shown as the other colors. Okay. And hopefully you can be convinced that these exponents are different from those of the 2D Ising model. So on this slide, what I'm plotting here is the sort of time-dependent value of the exponent that you would extract. That's what I'm calling theta t on this plot. And you can see that the values of these exponents that are being extracted are, in my opinion, quite comfortably different from those of the Ising model. Okay. And when you use this relation to extract the dynamical exponent, you get these values that are shown on the right. Okay, so Z sub A is the model A value, which is that of the Ising model, and then the others are the values that that we obtain numerically. Okay, so in particular, for example, for this M squeezing code, we get something about 1.4, which is quite significantly smaller than that of the Ising model. Okay, so what does this mean? Well, it means that these critical points actually define new dynamic universality classes that I don't think have appeared in the literature before. Right? Now, since the Ising dynamics, that of model A, is stable under RG, which I didn't go into detail about, but which is true from an epsilon expansion calculation, it means that these models actually must be at strong coupling. Okay, and in fact, they also must be fundamentally non-equilibrium. Okay, so they must not have an emergent equilibrium description. The reason why this is true comes from a nice recent paper by these authors, which showed that if you have a dynamical exponent less than 2, then you cannot have an effective equilibrium description. Okay. Okay, so I think that kind of wraps up the first part of the talk. Here are some examples of things that I'd like to think about. So given that we have these new non-equilibrium critical points, well, how do we come up with a theory understanding the universality class they're in, right? Me personally, I only know about KPZ and percolation. So what else is out there? How do we understand them? I'd like to have a better understanding of why mean field theory fails so drastically. I'd like to generalize these models to other symmetry groups. I think, anyway, there are lots of extensions that one can think about. Okay. That was part 1, which, as expected, went left me with about 10 minutes, but I think that's okay. I can get through this pretty quickly. So, but I don't have to. So people also feel free to keep interrupting with questions. So, in the second part of the talk, I'm going to discuss work where we used some numerical tools to find a large number of other examples. Okay. And it's done with these 3 co-authors. So Asan is a postdoc working on computer vision and artificial life at EPFL. Nathaniel is a grad student working with Ehud at Berkeley, and Aditya is a grad student doing QI at Caltech. Okay, so what we wanted to know was, okay, given we had these examples, like what else is out there, right? As a first analytic result, we can show the following. So if we have we show that if you have a cellular automaton which performs a majority vote on any collection of spins which is not invariant under a pi rotation, then it defines a robust memory. Okay, so this is like, for those familiar with Tomb's rule, you can think of this as a generalization of Tomb's result. But to go beyond this, right, what do we do? Well, the rule space of possible dynamics that we could consider is actually extremely vast. Okay, so if we just have a cellular automaton that takes a 3x3 input, 3x3 neighborhood of spins as input, the number of possible rules we could try is the number of functions on 9 bits, which is 2 to the 2 to the 9. That's way bigger than the number of atoms in the universe. So we have to find a efficient way of exploring this rule space. And the way that we have chosen to do this is using some techniques from computer vision and machine learning called neural cellular automaton. Okay, so what is a neural cellular automaton? It's essentially just a cellular automaton that's parameterized by a small neural network. Okay, and it's trained. You train this neural network to try to heal damages in input images. Okay, so I think for time reasons, I'm not going to have a chance to explain how this works, but I'd strongly suggest people to check out this paper by this Foundations of Intelligence team at Google, which is quite excellent, and which we just modified for our purposes. Okay, so what they did is they came up with a way of training translation invariant local cellular automata to stabilize particular images. Okay, so in this example, we have an image of a lizard, and I'm going to just play an animation of me erasing parts of the lizard. You'll see what happens. So this is me coming in and just destroying parts of the lizard's body, and it then subsequently like regrowing its the things that were erased. Okay. So I think yeah, again, please check out this paper. It's very cool. So we basically took this framework and used it to discover a bunch of new non-equilibrium memories. Yeah, maybe there's some details about the training that I'm not going to get into. And let me just tell you about the results. So we tried this training process about 1,000 times and found an appreciable number of new memories. The training runs that we did that did not find memories kind of got stuck on something that looks like the Ising model. Okay, but provided they didn't get stuck on something that looks like the Ising model, they found some new bizarre way of doing error correction. And let me okay, here's the typical phase diagram of the rules that we find. So kind of looks similar to the phase diagram of the squeezing codes that I talked about, except since we're discovering these in numerics, there's no particular reason for them to have any symmetry. And we generically just get some phase diagram that looks like this. Okay. Let me just briefly show you guys what this looks like. Oops. My mouse has disappeared. Oh, this is not good. Why is this happening? Okay, well, it came back. Sorry, this was not as smooth as I was expecting. Let me just, okay, now we're here. Let me show you what happened. So we made this website to kind of explore, to demo some of these memories, which you're invited to check out, memory NCA at GitHub. So what I'm showing here is just the evolution of one of these cellular automata under noisy dynamics. Okay, and this is one particular rule that we found, and it just happens to erase minority domains in this particular way. Okay. So this one kind of gets shrunk as some kind of triangular shape. And if we go to the other kind of error, we see this one is also getting shrunk according to some roughly triangular shape kind of thing. Here's another example. This one looks actually quite similar to the squeezing codes. The white minority domains are getting squeezed horizontally like that. And if we go to the other situation, we see that the black domains are being squeezed roughly vertically, right? And we also have some other examples. This guy gets squeezed in this particular direction, and its counterpart. Oh, it looks like I'm a bit above the noise. Oops. Okay, I'm a bit above the threshold there. That produced a logical error. Okay, I'll come back to this in a sec, but let's go to the next slide. One of the interesting things that we discovered from this analysis was the example of a noise stabilized memory. So what do I mean by that? Well, I mean that it has the following phase diagram. Okay, so it has a memory phase which is not monotonic as a function of noise strength. So if you imagine what's happening here, if we go to say a non-zero value of the noise bias and we increase the noise strength, we go from a disordered phase to a memory phase at larger noise, and then back to a disordered phase. Okay. So the memory here requires that you actually have some noise in order for it to be stabilized. Okay. So I'm not sure if I kind of forgot the settings that I need to make this work because I didn't really have a lot of time to prepare for this, but let's see if we can make it work. So what's going on in this automaton is that this is an automaton with this feature. The black spins are getting erased, as you can tell. But if we go to the opposite scenario where we have a black logical state and we're creating white spins, you can see that the white spins just grow and they take over. Okay, so this in the current settings is not actually a memory. right? Because the white spins are growing out of control. But it turns out we can stabilize this memory. Oops, okay, we're really killing it. We can stabilize this memory in the presence of sufficiently strong noise. So if let's see, so here it's growing, but if I crank up the noise strength, eventually we get to a state where maybe around here, it starts shrinking. So I think we can agree that this is going to shrink, yeah. So at this amount of noise strength, these guys shrink. And we also haven't destroyed the other memory state because these guys are killed, right? And so this realizes an example of a noise stabilized order, which I think is quite amusing. Okay, let me skip over that because we're pretty low on time and just come to the outlook for the second part of the talk. So one of the things I'd like to do is better characterize the landscape of robust dynamics, right? So I kind of produced a lot of examples. Some were found analytically, some were found using this machine learning framework. But how do they all fit into the landscape of rules, right? Do they occupy, what's the kind of topology of the rule space which defines memories, right? That's a question that we haven't really taken a lot of steps towards addressing. Again, I'd like to learn memories with other symmetry groups, right? Especially with U1, and to play around maybe a bit more with this technology, right? So here I'm showing a video of me interacting with a different type of a memory that we trained, and you can see it just stabilizes a bunch of bubbles that self-reproduce, right? So how the heck do we understand this from a physics perspective? I think that's a pretty interesting question. And then maybe going a little bit further is, well, the memories that I discussed today are capable of essentially homeostasis, if you like. So they can robustly maintain information in the presence of noise. But I think something that would be really interesting is figuring out whether or not there is systems which can robustly process and compute on information in the presence of noise, right? I mean, in some sense, the answer is yes, because this is what biological organisms do. But you know, can we realize phenomenon like this in simple condensed matter models and study them in the way that, as physicists, we would like to study them? I think that's a very interesting question. Okay, that's all I wanted to talk about. Thanks everyone for listening.
Yeah, thank you, Ethan, for the very fun, very interesting talk. Is there any further questions?
I have a quick question. So is there any analogy in a quantum version, like a QCA?
Analogy, do you mean, what do you mean by analogy?
Just like the quantum memory, for example.
Yeah, so well, quantum memories they're like harder to construct, and I don't want to say they're better understood. I think the reason why I say they might be better understood is that no one has paid attention to classical memories and classical information processing. So there were very simple examples like the one that I just talked about that had gone undiscovered. In quantum memories, the simple things like the four-dimensional Toric code, for example, have already been figured out. You can use these kinds of cellular automaton to create decoders for quantum memories. And I guess I've been doing some work on that, but maybe they're not. I don't think we've learned as much about physics from those in that setting as we have in the work that I just discussed today. So I have some examples of some quantum decoders which operate locally, but they're either very inhomogeneous in space-time, or they rely on having a noiseless classical support architecture in order to do error correction. And they're not perhaps like the physics of them is perhaps not as like clear cut and interesting in a statistical mechanics way yet. But of course, I think it's a very interesting direction to think about.
I see. Thank you.
Yeah, no problem.
Any further questions?
I have a question. Oh,
Mhm.
so for these like beyond equilibrium, um, you mentioned that these things are like beyond equilibrium or beyond detailed balance, maybe I should say. Do you know if
Mhm.
do
Yeah.
you know if there's a like a generalized detailed balance that these things could satisfy, like detailed balance followed by some internal symmetry or rotation or something?
Mm. Yeah, I think that's a good question. I don't know what the minimal way of breaking detailed balance is that would allow you to produce this phenomenon. So one thing that I didn't mention is that let me go back to just illustrate this guy. So we had this squeezing code, right? The dynamics of this squeezing code can be implemented using a time-dependent Ising model. So you take what you do is you do Glauber dynamics, heat bath dynamics under a Ising model where the couplings in the Ising model vary periodically in time. Unfortunately, I don't have the animation for that, but it's pretty simple to construct, and you can check out the paper for more details. That model breaks detailed balance weakly in the sense that the dynamics is always doing detailed balance with respect to a Hamiltonian, and the Hamiltonian, while changing in time, can change pretty slowly in time. So it's a slowly oscillating Floquet Hamiltonian that you're like locally doing detailed balance with respect to. That's the closest I've gotten. And for example, in the other memories that we looked at, you can prove that no detailed balance obeying process can describe the long wavelength physics, but how close you can get is a open question, I would say.
I see. Thanks. I had another question since you brought up like stuff like 40 toric code or something.
Yeah.
Are there like I mean I guess there are these classical analogs of 40 toric code where like information is encoded in whether or not like some classical loop transverses the homologically
Yeah.
non-trivial or not. Um,
Right.
and I guess I never but I never sort of wondered before, but I guess are these things also robust to like bias noise?
Yeah, so that's a very interesting question, actually. So you could I think the most concrete place to consider this is to take two-dimensional gauge theory, classical gauge theory, Z2 classical gauge theory in 3 dimensions, which has a
Right.
deconfined phase, and ask whether or not it's a memory in the presence of perturbations which break the gauge redundancy of the system, right? This exact question was addressed in a paper by Hastings, Melko, and David Poulin from like order 10 years ago. Nothing against any of those guys, but I didn't find the arguments in the paper extremely convincing. But there's going to be work coming soon from Yaodong Li and other people at Stanford showing that that is indeed a memory, even under with arbitrary perturbation. So that's basically the simplest example of an equilibrium classical memory, so a self-correcting classical memory. How to decode it, of course, is a very different matter. The memories we were looking at today, they just store information locally in the magnetization of the spins. For gauge theory, the information is stored non-locally, and yeah, I'm not sure what new physics we're going to learn from that, but indeed those are other examples. Yeah,
I see. Thanks.
no problem.
Yeah, those are all very interesting. Any further questions?
Thanks.
Okay, if not, thank you again, Ethan, for the very fun talk.
Yeah, thanks everyone for listening.
Yeah.
Have a good one. Bye.